Our guest today is Nando de Freitas. Nando is one of the world's leading artificial intelligence researchers. Born in Zimbabwe, bachelor's and master's from the University of the Witwatersrand in Johannesburg, PhD from Cambridge, postdoc at Berkeley, professor at the University of British Columbia, Vancouver, professor at Oxford, founder of Dark Blue Labs, which was acquired by Google/DeepMind, where he's a research director today. Nando has won a number of Best Paper awards at the top AI conferences. Some of his recent works include Gato, the first multimodal, multitask, multi-embodiment generalist agent, competition-level code generation with AlphaCode, learning to communicate, learning to learn, and playing hard exploration games by watching YouTube. Nando is very active as an educator and community builder for deep learning and artificial intelligence in Africa and South America. Nando, so great to have you here with us. Welcome to the show.
It's so exciting to be here. I'm a huge fan of this podcast. And so I feel privileged to have an opportunity to be here. Thank you.
I'm so honored to have you on. Now, Nando, before diving into today's conversation, I'd like to thank our podcast sponsors, Index Ventures and Weights and Biases. Index Ventures is a venture capital firm that invests in exceptional entrepreneurs across all stages, from seed to IPO. With offices in SF, New York City, and London, the firm backs founders across a variety of verticals, including AI, SaaS, fintech, security, gaming, and consumer. On a personal note, Index is an investor in Covariant, and I couldn't recommend any higher working with them. Weights and Biases is an ML ops platform that helps you train better models faster with experiment tracking, model and dataset versioning, and model management. They're used by OpenAI, NVIDIA, and almost every lab releasing a large model. In fact, many, if not all of my students at Berkeley and colleagues at Covariant are big users of Weights and Biases. Now, Nando, AI has become mainstream. It's something the world seems to have, especially with recent advances in ChatGPT and so forth, accepted as something that's really part of what the world is. Didn't used to be that way. It's a big change from our early days in the machine learning community. What do you think this will mean for most of the population on this planet?
It's hard to imagine. First of all, it's been such a big change since since I met you a couple of decades ago, and we used to go to Europe together and so on. And indeed, now everyone on the street is talking about AI. So it has become part of, I guess, the universal conscious. And what will AI do for all of us? I like still my favorite way to think about it is to think of it as a tool. And I hope for a family of tools that will allow us to do more, just like microscopes and telescopes extended the range, or personal computers for that matter, extended the range of things we can do. My hope is that AI will extend the things that we can do, whether it's to create new knowledge, whether it's to solve some of the hardest problems that we face, environmental problems, energy problems. And above all, I would love to see it being for the benefit of all humans, not just one particular group, but really for humankind. I think it's a natural progression that will be ultimately very important, I think, in sort of in the very long range of many centuries or millennia into the future will be essential for our survival. So I think it could be a wonderful tool, provided that we use it wisely and safely and with compassion.
Now, you are at one of the, many people would say, the leading institution for AI research today, DeepMind, right, based in London. At the same time, you talk about something that you hope will benefit the whole world. How are you going to make sure it plays out that way?
So one of the things that I've done, I guess each of us can do a little thing, and I think it's important Admittedly, I would not know how to do it, but all I can do is do a little bit. And I've personally been engaged in volunteering. So I love teaching. So I've continued doing that because that's the one thing I can do. And so I helped with the creation of the Indaba, raising funding and so on for the first 2 Indabas. I even helped going over the coding exercises and simplifying them and so on for the labs to run, and have runs the labs with the first Indabas. And also the Indaba, by the way, it's one of these meetings that we offer in Africa. It's a gathering of people, students, startups, and it's aimed at promoting artificial intelligence and the use of technology in Africa, increasing access for the African continent to AI. And that also inspired the creation of several other efforts across the world. One that I'm also involved with is KIPO in Latin America. So I also attended the first KIPO, and in a few weeks, I will be going to my first meeting in 3 weeks. 3 years. It's been a long time since I've traveled to a conference. And I'm really looking forward to it because it's being with the students in Latin America or in Africa is extremely energizing. And it is so important to go there beyond the content, beyond talking about cognits or whatever the flavor of the day is in AI. When students see you, and sometimes we forget who we are in AI, like, Pieter Abbeel, you're one of the greatest stars. I've always admired your work and so on. And millions of people admire you as well. So if you come to Latin America, if you come to KIPO in person, and not just give hopefully when in the future, and this is true of anyone in AI, I think most of the people you've interviewed in this show, just by being there and the students seeing that they can have a conversation with you, and they actually realize that, hey, this person is not as clever as I thought. I'm just as clever as this person, and I can discuss research with them. And that gives people a sense of empowerment that allows them to realize that I can also achieve that. I can go far. And I know this because I was one of those kids in Africa, and I remember talking to Professor Langbeer, who is this control guy from Imperial College. And for me, meeting as a student, a professor from Imperial College was like, I don't know, meeting the Dalai Lama or, it was an incredible transformative moment, because that's when I realized I could be part of that dialogue. And I couldn't overemphasize that, but it's the first thing you can give people. It's just the ability to believe that they can do it, that they can be part of it. And so that's a little bit that I do. And I encourage everyone watching this podcast to consider attending KIPO or Indaba or some of the meetings in Southeast Asia and throughout the world. It's really important, I guess, for us as especially senior researchers in AI to do that. And because that just allows for the community to grow there. And it's also important to kind of talk to the people there and the startups. There's a whole ecosystem that you want to grow. And it's also important that then that ecosystem starts growing, and that it's the people there that start leading it and directing it. And I've loved how the Indaba grew, and it led to many localized meetings, the Indaba X meetings, all throughout Africa. And it's the most wonderful time of the year when you go to one of these meetings and you're able to engage with so many young, ambitious people.
It's interesting you bring it up because a couple of things come to my mind, Nando. One, well, you you cleverly snuck an invitation in there for me. I'd love to take you up on that someday, even though this year I probably won't travel yet myself. But I look forward to it. Other thing that comes to my mind is when you talk about the energy, the excitement, while I haven't been to one of the events in Africa or South America yet myself, the Black in AI workshops bring a lot of the researchers to NeurIPS, right? And that workshop has tremendous energy. And I have to imagine it's a bit similar to what you're talking about, and it's absolutely amazing, the energy that's there.
Very much so. It's wonderful. We talk about the transformations that we've had in the field by going into, brought in by the GPUs or brought in by the transformers. But I think the people transformation has been equally amazing. I really love where our community is heading. I think there's a lot more work that we all have to do, but the work where we're moving in terms of diversity and inclusion, I think it's been one of the most important things that has happened to the field. And I just hope we can all continue to move in that direction towards making sure that our tools, our research, and so on capitalizes on what everyone can offer on diversity, and to ensure that it's an inclusive technology that we're building towards, an inclusive community. I think that's essential for what we want to achieve in the long run.
Now, if I can riff off of that, if I look at the current trends in AI, one of the trends is building very large models, right? And building those models is very expensive. So even though, we might educate people and so forth, educating might not be enough. We need to actually give people quite large resources in one way or another to be able to do those kinds of things. Or maybe there's other ways. Obviously the large models are not the only thing happening, but it is where a lot of the excitement is. So I'm curious how you think about that, how that trend interacts with everything you just said.
Yeah, I think you answered the question. The large models is not everything. I think the large models is a very exciting direction of research. We all know that extra compute allows us to build bigger models, and bigger models do tend to have properties that smaller models don't have, allow us to do certain kind of research that we can't do with small models. So the large scale empirical work that's going on in the world is sort of very important and is advancing us in big leaps. But at the same time, there's a lot of innovation that can happen outside, and that innovation can be in fundamental work. And we see this happening all the time. We all talk about attention is this corporate thing, but I do remember there was a student that came up with this thing. I remember interviewing the student in Oxford that had this attention idea, and then went on to visit the YouTube, I don't know, and then it went on to Montreal, and then developed the idea further with researchers in Montreal, with Korean Cho and Joshua, and eventually, it took many more iterations until the technique was fully, always gave birth to the transformers that we use now in the GPT-3. But it starts with a student coming up with this idea, and there's a lot more of these types of ideas. Recently we see these structured state-space models, and we also see a lot of work with differential equations. There's a lot of things in terms of fundamental work that I think people can do. There is other type of work that I think is very important, which is to how do we use the tools? Because even if we do have the good language models, and eventually I think we were going to learn how to serve them more efficiently and allow people to fine-tune them one way or the other. And if people can fine-tune them efficiently and have access to enough compute through the various clouds that, different organizations offer, then I think it does become possible to then address the next big challenge, which is what do we do with these tools? How do we make these tools useful in our communities? Because when you go, I go often, every year I go to Argentina and so on, I have family there. And I go to South Africa as well. And when you transport to those countries, you encounter a different reality, which is very different than, say, what you encounter in Berkeley or what I encounter here in London.
So Nando, I like how you're saying that, different parts of the world have different needs, challenges, and hence different opportunities to build AI applications, AI companies for that matter. Can you give some examples?
I can. And this is probably another reason why it's useful to travel and volunteer and attend meetings all over the world. When I went to the first Indaba, to give you an example, I learned about this phone app using like cheap phones that most people actually have access to. And one of these text apps is used to provide better healthcare. And one particular example that I thought was very poignant was where often moms will try to text a doctor to ask a question, like, for example, why is my child hasn't been able to eat? I give my child water. My child vomits, so is not able to stay hydrated. It's been one day or and so on. What do I do? And sometimes all it takes is a simple message and very simple piece of advice, just like boil water, and to be able to help that person. And because a lot of people around the world are dying of dehydration, very simple diseases that we don't even think about in the UK or the USA. And so, just sort of, and so then the next AI question for the startup was because we don't have enough doctors, how do we try to automate a system? So to be able to, and this is actually something now I would think with language models we could do a bit better, which is to provide help to people who are in need of that help. It's about enhancing what people can do. So one of the things I would hope of AI is that AI enhances every person to become, to some extent, better capable at providing first aid help or being able to deal with some medical conditions. And I think, that was a great example of a problem that I don't think about because I never encountered it here. But then when you go there, you realize it's a big problem. And you realize that with some innovation, you could actually save many lives. And of course, then there's many other problems that we don't even think about here. There's different economic systems, there's different security challenges, there's different economic problems, things to do with agriculture and so on. And it's only by being part of that world, by going there, by talking to people, that one actually learns about all these very interesting research problems and is able to actually contribute and hopefully be able to also really see the true benefits of our technology, helping most of the people on the planet.
I really like how much time you spend on just making sure you reach much more of the world than most of us end up spending time on, and then making it clear how we can also contribute, Nando. I feel a little pedestrian asking the next question in contrast to everything you just talked about, but I guess for people like us, a lot of the work that we see happen is coding. And coding can be very time-consuming and frustrating at times. because most people have a clear idea of what they want, but then somehow computer won't do it exactly right. And you recently were one of the big contributors to AlphaCode at DeepMind. Can you say a bit more about AlphaCode?
First of all, it was a wonderful experience to be part of it. It was a project done by a large team, and it was wonderful to witness what people were capable of doing. And so AlphaCode is, so every year, many schools, Berkeley is very good at this, and compete internationally or nationally and so on in these coding competitions where you're given a problem in English. For example, you have certain goods and you want to distribute them one way, which is the best way optimal way to solve that problem. And then very smart, the smartest students at coding and so on from all universities get together in teams, and then they go to these competitions, and then they quickly try to hack some code that solves the problem. And so from a perspective of doing research in AI, it seemed like a very interesting problem it's a good challenge because it's very easy to measure and so on. And it's of wide interest. How could we go automatically from that description to code that solves the problem? And so AlphaCode was an attempt at doing this. It capitalizes on using, no surprise here, transformers, and take that description as input and then generate the code. It uses a few other tricks like sampling many solutions, and it uses a lot of very clever ideas as to how to narrow down those samples to so that we have solutions that are able to, so we actually able to compete and get a reasonable success rate at writing code that addresses those problems. And it was truly remarkable how well it did. It wasn't perfect. I myself was looking at a piece of code, and sometimes I'm reading the code, and then there's a for loop doing a bunch of things, and then there's more code, and then you realize, why is this for loop here? And you realize it's just extra code that the machine created, and that is not used anyway. It's a bit like when grad students just throw everything in the exam, and some of it will be the solution, and some of it is things that they were thinking about. It's not perfect, but I love there was a blog that actually says that it's like, it felt like there was a dog in a room, and the dog was speaking English, but everyone was pointing the finger at this dog for not having proper grammar. And then that blog, I think, is best described how I felt about it. It was just, for me, it was amazing that it could do that, because I was a bit involved with the students doing these coding competitions at UBC 20 years ago or so. And so to see a machine doing that is just quite remarkable. And I think even one day, perhaps these machines will move on from having a performance of, say, being in the top 20% and so on, to actually being some of the top coders. And out of it, there's also, besides this sort of that challenge, that also has led to a lot of people, and not just DeepMind, but also many other places, including OpenAI and so on, to come up with tools to improve the workflow of software engineers and coders. And I find that I find myself nowadays, like, I type a P and it completely writes the whole print statement that I had thought about when I was debugging something. And it's here, it feels like, oh, it's reading my mind. But it turned out to be a very useful tool.
Yes, becoming very real. I talk with my students, and they have these code completion add-ons turned on pretty much all the time. It doesn't mean it always auto-completes correctly, but very often it does. And if it doesn't, then they can always not accept it. And apparently it speeds up their work tremendously as they're coding for their research projects.
It does, especially if you're not coding every day and you just dive in every week, maybe a couple of hours, then you're always a bit rusty of the syntax, but this thing just solves that problem for you. It's quite amazing how much it can improve your productivity.
Now, I think one of the things that's really interesting about the agents that can help code is the generality, right? It's something, coding is such a general thing. Compare that to something more specific, like learning to play maybe the game of chess or learning to play the game of Go. Those breakthroughs were very interesting because the methods were shared across the different games in the end, but the agents were not shared. It was a separate agent, separately trained, yes, with the same method, but separately trained, building its own neural net, essentially, to get the job done, and a separate agent, separate neural net for the next game, and so forth. And coding is much more general. And in fact, a bunch of your work is really pushing the frontier of generality, going from these specialist agents that are hyper-trained on this one thing, and sure, maybe can compete with humans on this one thing really well, but then it doesn't mean they really understand anything else. And so I think the Gato work that you recently published is a great example of pushing the generality to a whole other level. Can you say a bit more about what you did in that work? And also maybe what inspired you? What made you think that this would be possible? Because to me, it was surprising how well it worked and how it was such a general agent doing so many things with one agent.
Yeah, I mean, I think for many researchers, that's always been one of the dreams, is to be able to define one single intelligent system that is capable of doing. And I think what captures the imagination is that can do anything that a human can do, for example. And perhaps it can do other things, and maybe it does it slightly different or completely different than how a human would do it. But we've always aimed for this generality. In fact, people started calling AI AGI because to emphasize the importance of generality. And I mean, as you know, I was one of the people that attended the CIFAR meetings where the sort of deep learning came from, and right from the beginning. And I think within that community, within the Canadian Institute for Advanced Research, where I think you attended a few of those meetings, and Andrew Ng, and all these wonderful people you had in your meetings. There was always a connection with neuroscience, and so the moment you think about neuroscience, you actually realize, well, this piece of tissue is sort of very general. This piece of brain tissue, it can be used for perception, or it can be used for action. And even you see these implants where you can implant something with pins in your mouth, and with a camera, if you cut your vision, it's with time through these pins and depth processing, you actually start being able to tell depth without seeing. And funny enough, it's the visual cortex that gets recruited to do this still. Even though the sensation is tactile, it's haptic, it's no longer visual. And so of course, there's many works in neuroscience. It's a very old idea going back to the 70s, kind of pinpoint this, that there's perhaps just one universal algorithm that can do it all. And so then it does beg the question, when we have these new architectures and advances, are we now at the point where we can revisit that question, and how would we go about doing it? And I was fortunate enough to have encountered early in my time at DeepMind a colleague, Scott Reed, who's very passionate about the same things and who is incredible at executing plans and executing ideas. And it's also fortunate to have this brilliant team of young people who were very keen to make this happen. And so we spent 2 years on working on this. And at many points we sort of forewent, going for publications and so on, which is often a drive that we researchers have. And just to focus on sort of bringing in more and more, doing some of the boring stuff, like let's bring in more and more data sets, let's build more and more infrastructure. And that sort of, there's up and downs in that process, because sometimes you wonder, should we not just like speed it up and do this or that? And but so that's how the project came to be. And we just aimed to see whether we could come up with a single model, single big neural network that would be able to take all types of input, whether it's vision, whether it's dialogue, whether it's speech, whether it's, torques, proprioception and so on, and be able to either talk to you or control a robot arm. And eventually, well, you've seen the results. We've had some success with it. I think, but I do see that as a first step. I also don't see that as the only work. I'm very grateful for you thinking of it that way. I think it was one of the first. But you yourself came up with Decision Transformers, which is a very similar idea in spirit. And I think there were other ideas at the time, Sergey Levin and so on. But as I said, I think there's been a drive in machine learning for many years. And in fact, I remember discussing this at CIFAR with Andrew Ng, who was also very interested in these types of models. And in fact, that was at the time when, just before he went and started Google Brain. And it was believing in this dream that kind of drove that, I think, to some extent. And I think we still have a long way to go, but that dream is still alive. And I'm happy that people now see that it may be possible, and that there's more and more people interested in working on it. And of course, there remain many problems. There remain many challenges, many things we haven't shown. And but yeah, it's definitely something I'm excited about and that I plan to continue working on. And I think many other researchers, including yourself, are working on it now. And by the way, your recent paper, I have to put an ad here as well for all researchers to go and read Pieter Abbeel's latest paper, generating videos using YouTube videos. I think it's brilliant, and it's this kind of idea that I think will be very important to build more general agents.
Yeah, it's interesting. It's all very related. I think in the Gato paper that you wrote, yes, it ties to Decision Transformer quite closely, but I would say there's something fundamentally different, which is the insight that you can tokenize everything, and that people used to think of multimodal learning as there's this mode and that mode, and it's all its own thing. And you realize that if you properly, of course, the tokenization needs to be done right, but if you properly turn it all into a sequence of tokens, a single architecture can just process it all and generalize, which is really beautiful, I think.
Yeah, it's also based on the whole idea. I first tried to do something like that using a method called PAQ. So I think a lot of people might not know PAQ, but it was a method invented for text compression, and it was for the very long time state of the art. And so PAQ would take images and text and all sorts of things and would transform it to sequences, and basically sequences of bits. Until, if you wanted to be efficient, you kind of go to bits and you try to make the code. And then it used essentially context. It was sort of hand engineered features using the context of the string of bits to gate a neural network and predict the next bit. And then it's an architecture that consists of many neurons, and every neuron is just trying to predict the next bit. It's a very interesting architecture. So I became quite fascinated by it. At the same time that Ilya was working on his hessian-free RNNs as a student in Toronto. Mm-hmm. And so I remember working in this and trying to convince Ilya that he should switch from his RNNs to PAQ. But I'm glad he didn't, because that actually was quite fruitful. But but the idea was already there, where we were using a single model to deal with images, to deal with, and in fact, at the time, I think I was using an RBM or a sparse coding model, and then I was taking a sequence of the hidden units, and then I was doing PAQ with. By the way, I shouldn't say I was a student of mine at the time, Byron Knoll, who is now at Google and has continued working on this and similar ideas. And he was a brilliant coder, and he was able to hack all the stuff at the bit level, bit operations. But yeah, so that idea was the idea of using everything should be just a single sequence was already there in the literature. And so, Scott, I remember when I discussed this with him, he was very excited about it, and he definitely pushed for it. And he was a champion of this idea, DeepMind, and eventually succeeded with it. And I think actually Sergey Levine and his team, they also came up with a very similar model where I think they were also tokenizing everything to just use a sequence transformer. So it's very closely related to that. I think what we did differently perhaps is we actually devoted a lot of time to it. I think we might have started a bit early and started working on it, and we just made sure that we brought in as many data sets and as many tasks as possible. And that's a big challenge, because once you have, if you want an agent to do 600 things in environments, that means you need to be running 600 environments during your training. And that's a massive endeavor in evaluation and data processing and so on. So, one of the people that led this, Sergio and Gomez in the DeepMind team, I think he did wonderful engineering work. Gabe as well. Yeah, there were lots of engineers really working very hard to make that infrastructure possible, to be able to run those experiments.
Talk about generalist agents. Gato, we talked about, is essentially learning ahead of time from its own experiences, and then can do things later. We also did some work where you don't have to do all the learning ahead of time. You get to go watch videos, retrieve videos, which to me seems brilliant. That essentially matches what most humans do. If I have to fix something in the house, I will find a YouTube video that shows me how am I supposed to, fix this drain or something. I can't do very complicated things, but the very simple things. I go watch a video and all of a sudden I can do it, even though I've never done it before. But you've done this with AI agents. Can you say a bit more about what kind of capabilities did the agents acquire?
And so that in that early work where we, it actually started by me watching my nephew playing Minecraft, and he became very good at it just by watching. And I was like, but that's how we should be learning games. We shouldn't be doing reinforcement learning in an environment. There's so much content on the web that we should just learn from it. And now many people do that, and I think people have done it very well with Minecraft recently. But at the time I thought, let's try to do that. Let's try to capitalize on everything that exists out there. And of course, there is a question then of domain, how different are all the versions of Atari and YouTube from the simulator that you have. But if you do happen to have a simulator and you have many videos, then you can take advantage. You can do some transformation. So there'll be a small domain gap, but you can deal with that and then be able to sort of try things in the simulator environment and learn to play games. So at least for Atari, we were able to go and just watch videos of what's going on and then be able to play those games and be able to essentially, play them much better. I think that if we were using much more expensive RL agents from scratch, I think that paper that we did back then, that was sort of a taste of what could be possible. I often in research, I like to find problems that, that people haven't really tried them really hard and to show that something is possible. And because I think that's, just like when you inspire students and you go there and once they believe it can be done, then they will go ahead and do it. I think with research is a bit like that. If you can show that it's possible to do something, then soon after there will be a chain of other papers and products and so on that will far improve upon that. And I still believe that we have a long way to go in terms of taking advantage of that idea. There's still all of that video, as you said, on how to do anything on the internet, and we could take advantage of that video, not just to play games, but I think ultimately, as we're able to, especially now that we're building much better video models of the world, with diffusion techniques, with masking transformers and so on, I think we will soon see different realizations of that idea, where people really can sort of learn from how-to videos in YouTube, and they're able to transfer it to. I think that the most obvious thing is how to get robots to do different things, because it's as you know, because you have more experience in this than anyone, I think. Collecting robot data is very hard. We often see these videos of people teleoperating their hands of the robots and so on. But then when you actually go and try this teleoperation stuff, it doesn't really work. It's very hard to do good teleoperation. And of course, you're limited by how many humans have the stamina to actually teleoperate robots. And then there's this other thing that happens in the lab, which is you're teleoperating to collect data, and then your gripper breaks down, or you have to upgrade it because the company has a new gripper, and any of those changes in dynamics of the machine or in the appearance and so on just mean that you have to collect data again from scratch. And so it's very time consuming to collect data. It's also very wasteful to just have to collect again and throw data away. And there's, I think, even if we were to pull all the data from all the labs in the world, perhaps it's still. So eventually, you do have to go to YouTube, see how people do things, and then be able to come up with innovative ways of transferring that knowledge, so that the robots can actually just watch, just like we humans see others doing something and then we do it. I think that ability is something that I expect we're going to see a lot more of within the next few years. I think it could be transformational for robotics. I'd be curious to, I'm going to turn the interview on you. How transformational do you think it will be in robotics if the robots can just watch a human doing something and then are able to go and do it? What prevents us from, based on your experience, from doing that? Is the question, is it algorithmic? Is it hardware?
It's a combination, but I think if we can actually have a neural network that is sufficiently capable to watch a person do something and then know how robots should do it, I think it really opened up many, many opportunities. And it could be watching a person live in the same context, which would be a little easier, or it could be retrieving videos online from related contexts like we as humans do. We usually don't have a video where somebody did the same little fixing thing in our own house. It was a video in another house and doing something very similar, right? So yeah, I think when I think about robotics myself, it's essentially repeated motion robots solve problem for a very long time, building cars, building electronics, and so forth. But that's only 2-3 million robots in the world. Then you run out of opportunities for these robots because the rest of the world is not so repetitive. And then think what I'm doing now, warehousing and related things in terms of difficulty, farming, recycling. I think that's the current generation of things that are possible. But yeah, absolutely. I think what you're talking about is the next thing after that. And then you can, I think once you can do that, learn from one video how to do something as a robot, I think you can go into houses and be super, super helpful. There's a question, as you alluded to, Nando, everything's built for humans. Are the robot grippers general enough to do all the things we want them to do in a house today? Probably not. But maybe it'll give a very strong incentive for some really great electrical and mechanical engineers to dive in and build some robust human-size hands that then could do the similar things. So yeah, it's hard. It's kind of a weird question in many ways for me because it feels like it's been the goal of my research for like 10, 20 years. And it's kind of weird to think that maybe we could actually do this in the next, who knows, handful of years, maybe even sooner. I don't know.
In some ways, solving AI is easier than solving robotics because you also have to deal with the hardware question, and the hardware question isn't easy. And there's economic factors that also factor into the equation. Building machines is not actual machines is not cheap. I do think it's important. I still think robotics is one of the most important frontiers of research in AI and intelligent technology. Because I think, for dangerous activity, and so, when an activity would be too dangerous for a human, where you need robots, and these arise, especially when problems arise that humans have to deal with. Earthquakes and so on, as we're sadly witnessing recently. It would be really useful to have machines that could help in those scenarios. I also think ultimately, for space exploration, it also becomes really important to rely on machines because it would be very harsh for humans, say, to go to Mars and so on. But as you know, we can already send robots there and so on. So I think the robots are the first step. But I think if you do really one day end up being an interplanetary species, then robots will play an essential key role in that. They'll be the enabling technology that will allow us to achieve that.
Yeah, absolutely agreed. Switching from robots to a slightly different topic. As you've alluded to in this conversation in the past, it's particularly interesting to in research to push things that haven't really been shown much sign of life before, and all of a sudden you realize maybe there can be some sign of life here. Let's show something new. And a work that really stuck with me and influenced a lot of my work is your learning to learn work. You had this paper cleverly titled "Learning to Learn by Gradient Descent by Gradient Descent." And as I understand it, the big idea is that why should we write the learning program still? Can't the learning program also be learned, right? It's a recursive process in some ways. This paper is now from a couple of years ago. I'm really curious. Maybe you can quickly recap what you did in the paper, but also give your perspective on what you think about learning to learn today.
In terms of my experience with it started. So I was pointed to this paper by one of my collaborators, Misha Daniel. There was this paper by Smith Huber doing this with I think also with Seb of Writer, I think. And it looked like a wonderful idea. One of these ideas that was worth revisiting and doing it with our modern neural networks. I became fascinated by it because I think in as much as possible, I always believe in capitalizing on the data that we have. But sometimes I also find it interesting, just scientific curiosity as to how do things arise? How do things emerge? And in particular, I was interested in, I was philosophizing a bit. I was thinking of evolution as a learning process that then creates these biological machines that can learn. So it's a learning process, the dynamical adaptive process that has led to the generation of dynamically adaptive processes that are capable of learning amazing things like calculus and algebra. And so to me, it made sense that we needed to, endow our neural networks with that capability. And so we start working on it. We tried quite a few things, and it was a bit frustrating in the beginning because we weren't getting very far with it. And then Martin, who was a very young collaborator of mine at the time, Martin Andrzejewicz, who actually went to work with you afterwards and did wonderful work with you. He sort of persevered with the idea and eventually got it to work. And also, with the help of a few others, Sergio and so on. And then I became really excited about it because I thought, there's an opportunity here for neural networks to learn what the other neural networks should be like, what the algorithm should be. It's like we're still hand engineering a learning algorithm. Unfortunately, it's still Adam after many, many years that most people use. So we haven't been able to engineer anything much better than that. But there was the possibility that we could engineer better algorithms. So we could have a neural network generate new neural networks that would solve the problem. And that led to lots of brilliant ideas on learning to learn. There's an explosion of works in that area. A lot of those works actually came from Berkeley, from your collaborators yourself. And more recently, I actually do see that manifesting itself with the big transformers and the language models. So that's one of the emergent capabilities of these big models that has really amazed me, is that I still see them as, especially in the few shot, it's like when you pre-train your model, I feel like you've learned that initial thing. And then when you give, say, some context, especially if you're prompting it with a few short prompting, giving it a few sort of input example solution, and then you give an input example and you give it a solution. I see creating that context with a transformer during prompting as essentially basically, with your model, what you learned was the ability for you to be able to prompt the model so that it's learning from few examples. So I see that as like few short learning to learn at amazing scale and generality. So I think now I see that idea is actually happening a lot, and that's been one of the sort of really remarkable things of the big language models is to see this emergent capability. But if you start dissecting and doing the math carefully, it's not too far from the things that we were doing before with one-shot imitation learning and robotics. We didn't quite have the big models and so on, but I think the ideas were quite similar. Of course, there was a lot more constraint than what is now. It's just like one single big model doing it.
In language, a lot of the current work focuses on the very large models, right? And of course, they had some amazing successes, unprecedented capabilities. I mean, there's a good reason there's so much focus on them right now. But there's another line of work, which you've actually done some of the early work, which still fascinates me, which is where the AI systems learn to communicate in the context of having to solve problems together, and hence invent the notion of communication because it helps them be more effective. Maybe a bit the same way humans and animals have learned to communicate because it helps them survive better, helps them get more interesting things done. And it hasn't been as active recently, but I'm curious. I know I'm putting a bit on the spot here because you probably haven't prepared for this question, but yeah. What are your thoughts, Nando, on combining some of these things with the current large language models, or maybe even these things possibly in a few years supplanting today's large language models because somehow it's fundamentally more similar to how humans came to language?
Yeah, it's definitely worth revisiting that idea in this context. I think that would be a good project. It comes back to this question of, do you use all your data, or do you try to understand, take a more scientific view and try to understand how did language emerge? And which is still, I think, in my view, it's still an open question. We don't know how it is that we got to this point. So if you're pragmatic, you have to realize that we have all this human language produced by the whole human race through the years on the internet, recorded mostly. So you could take advantage of that to train big models. And why should we bother to go and do this other type of research? It's probably the same reason of why we do history, why we do many other things, because it's an unknown. It's something for which we don't know the answer, and I think I think many of us would love to know how language comes to be. And so that initial project that was led by my student then, Jacob Burster, the professor now in Oxford, and Yanis Asael, who is also now at DeepMind, trying to use multi-agent reinforcement learning and sort of created environments where the only way the agents could possibly solve the problems was if they were to send information to each other that was meaningful. And they also put some of these bottlenecks like sampling before the softmax and so on to force the models to use discrete communication if the channels were noisy. Because we wanted to know whether they would come up with discrete symbols or discrete representations to communicate more efficiently, to be able to solve the task. We also tried to see whether it would be possible for them to learn to sort of eventually combining these symbols in compositional ways, just in the same way that we compose with language. And that turns out to be very hard. And I think there's been some progress, but we still have a long way to go. I mean, one example that I love is, like in nature, you have there's this monkey, and I forget the name of. At some point, I knew the scientific name of this monkey. So East Africa, but they essentially have different. They have sentinel monkeys, and then when a predator is nearby, whether it's an eagle or a snake or some, can't remember. I think it's jaguars there too. If one of these animals is coming, they will produce a different sound that is indicative of what animal is nearby. And of course, the response of the monkeys will be different if it's an eagle or, if it's an animal or a predator on the ground. If it's an eagle, they can just jump up a tree. But if they're on the canopy on top, then, they become, if it's an eagle, they're shooting up the tree because they don't want to, they could be vulnerable from the air. So they will do something appropriate to safeguard themselves from the predator. And so it's easy to build an RL system where the agents will learn to do that. The thing that was very hard to figure out for me is the next step, when eventually one monkey sort of learns to manipulate that symbol or starts thinking, I would like to get all this food, but there is this other monkey that I don't like, and I don't want this other monkey to get my food. And so maybe I will just tell this monkey that it's a tiger, even though it's an eagle. And then that way I can get all the food.
Cowboy.
I mean, that's a rather deceitful way to stop intelligence, unfortunately. But a lack of a better example, that it's being able to then sort of reason about those chants, to go to that sort of high level of abstraction. It's when just the sounds, the discrete symbols sort of transcend the immediate material, and then we can start manipulating them. Just like we humans use words, or we come up with these figure eights that are horizontal, we call them infinities, and when we manipulate them, and we're able to create knowledge about things we've never seen in the universe. And eventually we see those things with some fancy telescopes. It's so much of science has come, especially cosmology and so on, has come as a result of us manipulating these abstract symbols. We can make predictions that are so far beyond anything that we can see or will ever experience. And how you could create new symbols, create new knowledge, that I think is still a big open question, and it perhaps is going to become very relevant for language models, which is not just to paraphrase what humans do and so on, or sort of just combine what text there is on the web, but it's actually language models that maybe sit down with coffee and start thinking about the mysteries of the universe and start creating new symbols, new abstractions that allow them to then do some inferences and be able to make some predictions about the universe and be able to also come up with testable ways to verify those predictions. So I think invariably we will revisit this question of learning language, which of course has a lot to do with learning to communicate.
It's very interesting because you now talk about agents that could actually run experiments, right? Don't just output text, but would maybe press some buttons somewhere either on a website or maybe physically be incarnated in a robot, try things out in the real world, see what happens, and from that make new hypotheses and learn faster, hopefully, than they could otherwise, and have a deeper understanding of how things work. That's really fascinating. I'm curious if we kind of zoom out for a moment, Nando. When you think about the next, let's say, 5 to 10 years in artificial intelligence, what are the things that you are most excited about?
Well, I think a lot of the things we've talked about today, I imagine everything we've talked about today. I think the mainstream discussion now is, of course, on big language models. And of course, the questions, important questions arise there. How do you make the language models actually be factual and accurate? So this question of truth. There's questions about how do you make these technologies actually safe? How do you make them truly useful for humans? How do we, and then there's engineering questions. How do we make sure that important engineering questions? How do we make sure that we train them with a lot less energy? How do we make them also, cheaper, easier to access, and so on? And of course, all that comes with security and safety, and also how do we contextualize them? Because we were talking about communication and language. So there's different types of communication. Sometimes there's communication where like, for example, you're interviewing me here. I know that at this point you don't want to just chit chat, and I shouldn't just go and start telling you, about what I ate for lunch today and spend the rest hour of the day in that conversation. I don't think the viewers would appreciate that. And so the context is, to a large extent, determines what you talk about. And of course, context comes in many ways. It could be where you are. It could be who you're talking to. And I think that's something where we need to make progress on. And of course, and I do think we're going to see a lot of progress because there's a lot of driving forces that will make us go in that direction. Also, I'm interested in the sort of scientific question, the sort of experiments that we're talking about. And in particular, I'm thinking of the experiments that we do in our minds, these thought experiments, like Einstein used to talk about, imagine someone traveling at the speed of light and so on. This is something that I would hope one day the language models could do, because a lot of the experiments with physicists do, for example, cosmologists and so on, the sort of thing that Stephen Hawking was good at. These are experiments you do with pen and paper. And so provided you have a way of using tools of externalizing knowledge, of storing externally, retrieving this knowledge, and provided that then you can sort of group things and create new abstractions to be able to sort of talk about problems, I would hope that we would see a lot of scientific progress. And I think that scientific progress would, can you imagine if the machines start telling us, no, guys, you had this all wrong with how to build fusion reactors. Let me tell you, I've spent the last few seconds thinking about it. I derived the equivalent of knowledge of humans physicists for the last 200 years. And here's my conclusions to how you could build this nuclear reactor. And you can, I've created a simulation for you, go and test it, verify that it's, check my idea. This is what you need to do to verify it, and so on. Here's some tests. It would be wonderful. And we're starting to see that a bit in biology. There's been a revolution in biology. Right. Obviously I'm extremely proud of AlphaFold. With AlphaFold, we've seen a lot of biologists getting very interested in neural networks and machine learning. And so we see a lot of work on these nanomachines, on proteins and so on. And we're not quite there, but I would hope the neural networks eventually, with the ability to think about problems and reason about many complex variables and be able to derive new knowledge, just like we do by reasoning, by abstracting, and maybe by advising on what experiments should be conducted, what machines could be created. That's what I would hope this will take us. Because, if it takes us to solving our energy problems in getting safe fusion reactors to bring energy to the entire world, that would solve, the problems of famine and so on, and economic problems. Or even, reason about, we're starting to see a lot of climate models, better climate models than we had in the past. And it would be interesting if the models could reason and help us, make better predictions as to how we could go up, what kind of interventions we could do to ensure that we protect our environment. And even economic systems. I think economic and political systems are very, very complex, even for well-intentioned policymakers to be able to comprehend, to make relevant policy. So if the machines could assist people to come up with better economic policies, better environmental policies, and so on. I think that would be wonderful. That, I think, is sort of the mainstream. At least that's my dream of where I would love to see this going. And of course, a lot of this is...
That's beautiful, Nando.
Augmenting scientists, but I also would like to augment the people who are doing labor. So my parents, they just went to work. And in fact, as a kid, I would go to work with my dad. I worked in construction and as an electrician. And it's hard work. And for most people on this planet, you don't go to, we are so lucky. I go to work to explore ideas, and I have this, I'm so fortunate I work in this wonderful environment that is full of these incredibly smart people who love to explain things to me and brainstorm with me and so on. And we're just having these big dreams, and I get the opportunity to talk to people like you and be in podcasts and so on. But for a lot of people on this planet, you go to work to bring home the bacon, to make money, to look after your families and so on. And sometimes it's a lot of hard work. And sometimes you're very tired. And sometimes you break a toe or something, but you still know you have to go to work, and even if you're in pain. And that's the reality for most people. And so I think for a lot of those tedious tasks, it would be important to help people with, again, but that will involve hard work. That's where robotics comes in. And not necessarily replacement of labor, but just machines that are meant to make it easier for people to do their jobs, or that allow them to focus on more creative endeavors. I think the job market for sure will be evolving in the future. But what I think it's important is that if we evolve all the privileged jobs, and that we don't forget to also make sure the jobs for the less privileged people also evolve, so that they can have much more meaningful lives, perhaps spend more time with their families. And of course, with this, I understand that this is very utopian, and I'm not touching the questions of economics or motivation, psychological factors, and so on. But these are also the things that we need to work on all the time.
It's really beautiful, Nando. I would like to ask you one last question. I know your path in terms of PhD at Cambridge, postdoc at Berkeley, professor at UBC, then Oxford, and then your own startup, ending up at DeepMind / Google. But before then, what was the original thing that got you excited about artificial intelligence?
I was just lucky. I think a lot of things in life are not decisions you make, but just you find yourself in a context and you make the best out of that context where you are. Often I couldn't say that I planned things very far ahead. Maybe I planned to do a degree, and then I knew that was going to last at least 4 years. So, but quite often you encounter yourself in a situation in life, whether it's a challenge or an opportunity, and you have to identify what you should do. I was lucky enough that when I was in my third year in undergrad, there was a project on neural networks, and my control professor, Professor McLeod at the University of the Witwatersrand, and I was like, what are these? So I went to the library. So at first I thought, oh no, I don't want to do this. It's going to be one of those TCP/IP protocol things. I'm going to hate this course. But it was a completely different kind of network. Sort of, you open the book and there's a picture of a brain. And I think that's it. I got hooked. There were a few books in the library there, and I just couldn't stop reading about it. And then I had to go in MATLAB and implement my backprop. And yeah, back almost 30 years ago.
Yeah. Right exposure during your undergrad studies.
I was lucky that I had that opportunity.
Well, Nando, I feel really fortunate you had the time to come on to the podcast. Really enjoyed the conversation. Thanks so much for making the time.
Thank you so much, Pieter. And I love your podcast, and it's been a pleasure to listen to it through the years, especially during the pandemic and so on. It was always a good companion. It's a wonderful job that you do. It really brings what we do to so many people.
Thank you, Nando. Really appreciate it.